Atmospheric drag on an object entering the upper atmosphere does not apply a constant force. As the velocity shifts, the friction acting on the craft changes continuously. When engineers model these dynamic forces, they generate nested, nonlinear differential equations. These specific expressions cannot be solved using standard integration tables. The math does not map to baseline formulas. This is the mathematical abstraction of the problem. It is an integral pattern where a nested function is paired with its own derivative. The f and g components represent interlocked physical systems that must be mathematically decoupled. To separate these parts, mathematicians use a method called integration by substitution. Conceptually, this method is the operational reversal of the chain rule of differentiation. By reversing the chain rule, engineers can transform the independent variable within the equation. That transformation takes complex domain physics and collapses them into standard analytical forms. This mapping is the method used to resolve nonlinear systems across aerospace, electronics, and computing. To use substitution, an engineer must first identify an inner function within the expression, whose derivative is also present in the integrand. Looking at our nested equation, we identify the inner function, g of x, and its corresponding derivative, g' of x dx. The first step is declaring a new variable. We extract g of x and set it equal to u. Next, we differentiate the system to isolate the derivative, converting g' of x dx into du. The system undergoes a structural collapse. The complex integral simplifies into the compact expression, the integral of f of u du. This simplification changes the nested structure into a form that is ready for evaluation. The simplified integral now matches the baseline formulas found in standard integration tables. From here, the integral can be evaluated cleanly and quickly, providing an exact answer without using computational approximations. The final step is to reverse the initial transformation. We take our original g of x parameters and substitute them back into the solved equation in place of u. This final string is the exact analytical expression of the original nested system. By temporarily altering the independent variable, mathematicians bridge unresolvable calculations to arrive at exact usable states. We can apply this theory directly to physical engineering, starting with aerospace dynamics. Consider the aerodynamic drag acting on a spacecraft in orbit. The acceleration forces in orbital mechanics depend strictly on the velocity of the vehicle. This yields a specific differential equation of motion, where acceleration is modeled as negative k times velocity squared. To integrate this equation, variable substitution is applied to isolate the state variables. Once isolated, engineers can compute the integral to find the exact physical position or the elapsed time. The same principle governs electronics, specifically in the design of alternating current signal processing filters. Here, engineers must calculate the root mean square voltage, or total power dissipation, over a periodic waveform. These waveforms generate integrals with nested frequencies that require analytical separation. This graph shows an oscillating AC waveform and its corresponding integral. Using substitution, we map sine to u and cosine to du to solve the expression. Resolving this substitution yields the exact energy transfer over a single cycle. Whether calculating orbital drag or AC power, variable substitution is the standard approach for resolving these physical cycles. In statistical machine learning, substitution is used to manage continuous probability distributions. Analyzing continuous space requires working with complex probability density functions. Before these functions are used for training, they must be mathematically normalized. Normalizing a raw Gaussian distribution requires exponential scaling across continuous space. This 3D spatial grid shows a raw, off-center Gaussian distribution. We apply a substitution, where z equals x minus the mean divided by the standard deviation. This substitution rescales the data. The formula physically pulls and reshapes the raw curve across the grid. The raw curve morphs into a standardized normal curve centered at 0. This transformation allows statistical machine learning models to be trained on standardized data. Modern engineering pairs these analytical derivations with automated programmatic execution. Engineers use symbolic computation libraries, such as Python SymPy, for this automation. These libraries are programmed to recognize the pattern of a function and its derivative. Because the software follows the exact calculus rules of substitution, it does not rely on numerical approximations. The scripts output standalone analytical expressions for immediate validation by the engineering team. Reversing the algebraic chain rule provides the mechanism to decouple nested functions and scale complex data. We can determine orbital drag, filter AC signals, and standardize machine learning probability distributions. Integration by substitution is the bridge that translates nested physical systems into solvable computational logic.